All right, thank you, everyone. So I'm going to talk about some modeling, some hydrologic modeling, work that we're sort of introducing as part of our platform at the Oak Ridges Moraine Groundwater Program. So it's up, it's out, it's running around on our websites there. But I really want to talk about why I sort of created this. I'm not using a real off-the-shelf model. I'm using something that's kind of been my brainchild for the last decade or so. But really what it amounts to is we're trying to project groundwater recharge at a regional scale, but with some fine resolution. And you know, right off the bat, for you modelers out there, you might appreciate that that's a pretty hard task to do, at least in terms of getting the data and having it all run and having it run in a timely manner. So just an overview, just going to go through some of the services we have, and this is not like an ad or promotional thing. You'll get to understand or appreciate why, well, by the end of the presentation, why I created this model. And then just some of the challenges that we have faced, or at least the source water protection modeling community has faced in terms of maintaining models. And some of the extra bits that we found important to add into a recharge model. So first and foremost, just one product we have that is often used and is just a simple interpolation of shallow groundwater within our region. And from that we can just do a simple interpolation of where would we expect groundwater at surface. And what we do see is quite a bit of the area in our jurisdiction of the Greater Toronto Area. A lot of it has some potential groundwater discharge areas at surface. And so this is a challenge with any sort of modeling. On top of that, we have a functioning climate data service. So our entire region now has, you can click at any point, any location, and get a long-term infilled climate data set. There's a whole suite of details on how that's produced. You can have daily data or 6-hourly data, and they go back to 1901. And this also works at a point, but it also works within a catchment area that you can delineate to get the aggregated climate data within that data set. So we have some good data coming in. Another sort of program that we facilitate is called the Numerical Model Custodianship Program. This has been going on for the better part of the decade, and we are basically a library of all the source water protection models that have been created within our jurisdiction, and we have a program to ensure that they are all in an operational manner, and we offer the platform for someone to request that model and that we share, so that knowledge that was built into these models in the past tend to get preserved. And so last year was pretty good. We got 8 requests to share models, and they get worked on and they get reported and we get it back. So we just keep preserving that knowledge, because models are really sort of an organic knowledge base rather than just a one-time product that deserves to go on a shelf once they're done. So yes, we have all these models. We have all this climate data to support them. But the problem is these models are getting 10 years old, and the prime input to these models is groundwater recharge, of course. And as the models age, so does our groundwater recharge predictions. And we're clearly seeing some trends within our region that really require an update to the recharge, but that also requires a whole new set of modeling, of hydrological modeling to project that recharge. So just to go through some sample issues, this is a very coarse sort of plot, but I just sort of built this for the presentation. But just looking at it's not just floods, it's not just extreme temperatures, but it's also how that's impacting on, sort of on a day-to-day time scale. So what you're seeing here are just those days with which a minimum temperature is below freezing and a maximum temperature is above freezing. And so this is important because this is where that dynamics of that phase change of liquid water to solid water happens. And this is a big recharge event. So rather than having a snowpack gather like we're seeing this year, it tends to melt and sort of spread that recharge out and not become a spring freshet event. And so overall, over the last 50 years, it's about an extra day a decade. But if you do sort of focus on the later years, it's getting to be about an extra day per year. So, things are changing, and this is going to have an impact on recharge regimes, especially those areas that are really dependent on that spring freshet recharge event. Similarly, too, over the Oak Ridges Moraine area, we see a significant increase in wind speeds and wind gusts, and this can have an impact on evaporation rates and whatnot. So currently we're about a standard deviation over the long-term mean. And so again, once you plug those into a model, things start to change, your recharge patterns start to change, and this needs to be reflected in our groundwater models. The other aspect, too, is that when we have been looking at a lot of our shallow groundwater monitoring and some of the deeper wells, we see very rapid response to climatic events. This hydrograph here looks like a stream flow, but this is a shallow water well. This is 4.5 meters below surface. And I love this plot because you could see it superimposed with both rainfall and snowmelt events, and there's a clear connection here. So we need models that also represent that recharge at some sub-seasonal time scale to get this sort of quicker response in groundwater. So we have these models, we have the climate data, and we need to update the recharge. What's the problem? So this is going back to the potential discharge areas. The models that have been used for source protection, at least the hydrological models, don't have groundwater in them. So really we have to do these tricks as modelers to say a wetland is impervious like a parking lot, or just try and impose based on what we know of the region where groundwater is going to reject kind of recharge from happening. But it's not necessarily static like that. There's seasonality, there's hydro periods, which we'll hear coming up next, but there's also the concept of runoff generation in general. The models typically take an approach where you're just sort of saying, if the rate of rainfall exceeds the rate of infiltration, you get runoff. I don't really think that's the case in our region, primarily because we don't get the intensities that a lot of those models were empirically calibrated to, or designed for. So I look more to what's called this variable saturated concept, variable saturated area concept. So this is just the idea that as the ground saturates, the area of the watershed that's receiving rainfall is rejecting that rainfall, and that's where the runoff is generated. It's a groundwater phenomenon rather than an infiltration rate phenomenon. But again, these models don't handle that. So what we are left with, there's a bit of a dichotomy here. We have your standard hydrological models where we don't have the groundwater representation. And about 10 years ago, we started moving into the integrated models. These models that are both surface water, groundwater. Great, there's going to start rejecting all that recharge and getting that surficial, that interaction, that dynamic held down quite well. The only problem is that they were very slow. They were hard to calibrate, they were hard to do uncertainty analysis, and they still are slow. So I started going back and thinking, well, how can I get a hydrological model that does do some groundwater, have the groundwater effects to reject the recharge, get that variable saturated area type mechanism in, but make sure that it is fast, to make sure that I can run it as a hydrological model. And this will just help me get a better sense of recharge, the seasonality of recharge, which ultimately works well when you are inputting this into the groundwater model. If you put too much recharge in areas where there should be discharge, the groundwater model doesn't really like that too much, and you end up rejecting a lot of recharge, and anyway, the whole balance gets off. So here we go. So right now we have a model, and this model does do conceptually a groundwater discharge. You can click on any of these cells. There's 12.6 million of them. and get a seasonal hydrograph of your typical water balance numbers, precip, ET, groundwater recharge versus discharge. So it's kind of the same element. It's an exchange or a net recharge. And runoff. So just to look, what's great about our area, we have the model's calibrated across a 40,000 square kilometer area. So we were able to capture close to 200 stream flow gauges. But we're not here to talk about runoff, we're here to talk about groundwater. So the nice thing too is, because this is an integrated groundwater surface water model, integrated in the sense that we do have some groundwater response, I can also calibrate the model to groundwater monitoring, shallow groundwater monitoring. And shockingly enough, it seems to work a lot better than it's working on the surface water stuff. So, here's some good examples. They're golden examples, I'll admit them, but nonetheless, it is capturing seasonality. It is even capturing long-term trends, as we see, earlier periods of the decade that, had shorter recharge or fewer recharge volumes. But really what I'm proud about this model is I also, knowing we had to do so many calibrations, knowing, trying to gain an appreciation for model uncertainty, the sensitivity analysis, and having a regional model with large scale, with lots of parameters, lots of different variables going on, I needed a model to go fast. And so I started going to the drawing board and, coming up with, certain principles and certain constraints with which I would design this model. And by the way, I should say none of the components of the model is any way novel. I'm just piecing the right pieces together to make them happen. So basically, I don't know if you're into computers like I am, but often I would run these models and I would look at this what's called the task manager, and this will sort of tell you how much of your computer is actually doing the computing. And I'm not to be unfair to Geisha and hydrogeosphere. I mean, everyone had this issue. Is I'm only seeing 30, 50, maybe 60% of my computer being utilized, whereas what's wrong with the other 40%? And so the bigger one on the left is you can see where I started that model, and it's just cranked, right? It just runs, and I'm getting full utility out of that model. So the other comparison then is run times, like how long are these models taking? So I have a suite of examples here. We have the lumped model. This is the classic, here's a watershed, and you got a parameter certain parameters that fit in just to that watershed. We got artificial neural networks, so getting into that AI game. We got some semi-distributed models. This is the HBVEC is a template from a Raven model. Raven's out of University of Waterloo here. We got PRMS, that's out of the USGS and EPA, I think. And we have two sort of more specialized models. It's Geisha, which is a distributed shallow water equation model, so a flood routing model. And we got hydrogeosphere, which is sort of the cream of the crop, the integrated model, groundwater surface water model. And we see mine at the end there. So really what I'm looking at is just a basic comparison of, I took sort of the same sort of area, and here's how I would approach modeling that same sort of watershed with the same model, or pardon me, the same computer. And basically, this is sort of the idea of like, how long is it going to take to run that model? But it's not really fair because the lumped model is just one watershed. PRMS is a distributed model. Geisha and hydrogeosphere are a distributed model. I'm a distributed model. So it's really worth sort of comparing how many time steps per computational element, could be an HRU, could be a model cell, could be a finite element, and sort of divide it that way. So looking at how many things that can compute per second per time. So Of course, I could always adjust these models, and this is what we do with some of the slower models by making them coarser or extending the model time step. And this is where you can make your gains based on the design of that model. I didn't add mine because like mine was just blowing everything out of the water. So basically, it's not just to say anything specific to my model. Like I said, like none of the formulation, nothing's novel in there. I just took a different approach. I called it a pragmatic approach, knowing that I need these models to speed up. I, just based on different processes, how I interacted with the data, what type of language I used to code the model, all came in to give me quite massive gains in performance. And this is a practice that could be used with many other model types. So basically, what I've created is an integrated model, a groundwater surface water model that is built to be fast. It's not, it doesn't have all this is meant to supply recharge to a groundwater model. It doesn't do particle tracking. I can't do drawdowns and whatnot. But nonetheless, I can still incorporate groundwater information into the calibration of this hydrological model. And with that, I will say thank you.